The recruiter has spotted his eyes on an interesting person, Mark, an intelligent mathematician, wherein he will test his skills on whether or not Mark can answer his questions right.
To enter the games, you must win against me in Dokti. But every time you lose, you get slapped in the face.
I see. I accept your challenge.
Please pick a card. Each card has a designated question, and if you get it correct, you get prize money.
The recruiters given Mark a piece of paper. What's written at it is what follows, and we can see how Mark's fascinating brain works under pressure. To answer the first question of what is the probability that a soldier is wearing a square mask and carrying a baton, we are given that 25 out of the 100 soldiers wear a square mask and carry a baton. So, the equation for this is we can use probability of A is equal to 25, which is the squared mass soldiers that also have a baton. And out of that 25, we divide it by 100, which is the total population of pink soldiers. Divide it, we get 0.25 or 25%. For the second question of what is the probability that a soldier is wearing either a square mask or carrying a baton? We can use the formula for the union of two events wherein probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Now, we have to substitute these parts wherein the probability of A is the probability of wearing a square mask, and the probability of wearing a square mask is 60 over 100, which equals to 0.60, plus it by probability of B, wherein it is the probability of carrying a baton for both square and triangle mass. So we know that both square and triangle mass is equal to 100, but only some of them have a baton. So for the square mass, only 25 of them. Triangles have only 15. So we just add them both. 25 plus 15 equals to 40. And 40 over 100 is 0.40. We put that here. Minus it by the probability of wearing a square mask and carrying a baton, given in the first problem, which is 0.25. And we get the answer of 0.75 or just 75%. Now, for the last question, what is the probability that a soldier is wearing neither a square mask nor carrying a baton? The complement rule states that P, a probability of neither A nor B equals to 1 minus a probability of A union B. We can substitute the value of the earlier answer of 0.75 to this one. Since we get 0.75, 1 minus 0.75 is 0.25. And again, it's 25%. So, to conclude it, 0.25 or 25% wears a square mask and carrying a baton, and 0.75 or 75% of them wearing either a square mask or carrying a baton. And lastly, 0.25 or 25% wears neither a square mask nor carrying a baton. Mark was given another piece of paper. To answer the sub question A, we can multiply 3, which is the group required number of groups, and 6 as the required players for each group, and we get 18. We divide 18 by 255, which is the total number of players. 255, and divide it, then we get 0.007 or 7%. Now for sub question B, what is the probability of being in a group of 7? We can do the same as earlier. Multiply the number of groups, which is 27, and the required players for each group, which is 7. Multiply this, you get the product of 189, and divide 189 also by 255. Then we get 0.74 or 74%. Now, for sub question C, what's the probability of being in a group of 6 or 7? Since there is an or in this sub question, we can use the mutually exclusive formula, which is the probability of A union B is equal to probability of A plus B plus probability of B. And now, since we answered the earlier ones, which is the group of 6 or 7, we can use probability of A as, we can represent probability of A as 0.07 or 7%, and probability of B as 0.74 or 74%. We add them both. Then we get 0.81 or 81%. Now for D, what is the probability of not getting in a group? So we know that the total amount of players is 255, and it equals to 100%. Then we can use the earlier equation of the mutually exclusive formula, which is 81%. We can just subtract 100% by 81%. So 100% minus 81% equals to 19%. And that's the total number of players of without a group. Mark was given his third paper. What is the probability that player A hits the can at least once, either in the first or second throw? So first, we have to convert every percentages into decimals, wherein the chance of hitting the can on the first throw is 70% or 0.7, and the chance of hitting the can on the second throw is 50% or 0.5. The probability of missing both throws is 1 minus said numbers, wherein for the first throw, the probability of missing is 1 minus 0.7, which equals to 0.3. For the second row, the probability of missing is 1 minus 0.5, wherein it's as 50% chance of missing that row. So, to get the probability that player A misses both rows, let's multiply them both. Letter A, probability of missing both rows is equal to, let's multiply 0.3 to 0.5, since that's the probability of missing both rows. Which equals to 0.15 or 15%. Now, for the second one, probability that player A hits the can at least once is the complement of missing both rows, wherein P, probability of hitting it at least once, is equal to 1 minus probability of missing both rows, wherein it's we use this part here, 1 minus 0.15 equals to 0.85 or 85%. Now, for letter B, what is the probability that exactly 2 players out of the 4 hit the can at least once? So, we can use the binomial probability formula, wherein we should get the probability that a player hits the can at least once, which was previously answered in the last question, which is 0.85. And the probability that a player does not hit the can, we can get it by probability that a player doesn't hit the can at least once is equal to 1, representing 100%, minus 0.85, which equals to 0.15 or approximately 15%. And now, to get the probability that exactly 2 players hit the can at least once is probability. We can use the binomial probability formula, wherein the probability of exactly 2 players hit is equal to 6 times 0.85 raised to 2 times 0.15 raised to 2. It is 0.0978 or approximately 9.78%. Mark was given his fourth and last paper. What is the probability that player 456 successfully crosses all 3 zones and advances to the next round? So, to answer that, let's label it first. A. Each zone success probability, for the first zone, we let's label it as probability of S sub 1 is equal to 1 minus 0.40 equals to 0.60 or 60%. That's the survival of the first zone. Now, for the second zone, let's label it as probability of S sub 2, 1 minus 0.50 equals to 0.50 or 50%. Now, for the last zone, let's label it as probability of S sub 3 is equal to 1 minus 0.60 is equal to 0.40 or 40%. That's the survival rate at zone 3. Since the zones are independent, we can multiply the probabilities wherein uh, the probability of S sub 1 is intersecting with S sub 2 intersection S sub 3. So let's use this formula. Probability uh, probability of S sub 1 intersection S sub 2 intersection S sub 3 is equal to the probability of S sub 1 times probability of S sub 2 and probability of S sub 3. And now, we multiply them together. 0.60 times 0.50 and times 0.40, which equates to 0.12 or simply 12%. Thus, the probability that player 456 successfully crosses all three zones is 0.12 or 12%. This is the probability that player 456 gets tagged in both zone 1 and zone 2. Since player 456 failed zone 1, let's put that there. Label it as probability of failing zone 1 is equal to 0.40. And since he has failed zone 1, failing zone 2 is the probability of uh, F sub 2, probability of F sub 1, wherein it equates to 0.65. And since zone 2 is now dependent on zone 1, we can conclude that the probability of F sub 1 is intersection F sub 2. Probability of F sub 1 intersection F sub 2 is equal to probability of F sub 1 times probability of F sub 2 F sub 1. Let's input our values here. 0.40 times 0.65 and multiply them together, we get 0.26 or 26%. Thus, the probability that player 456 gets tagged in both zone 1 and zone 2 is 0.26 or 26%. Go.